Hello, I'm Chen. Today we are going to talk about our journey to understand how input modality and task geometry could affect the precision-first 3D drawing in virtual reality. As we all know, the capabilities of drawing in 3D unconstrained immersive virtual environment is a key primitive to unlock a wide variety of VR-based applications. For example, the designers could use such 3D drawing capabilities to efficiently externalize and communicate their ideas. Such 3D drawing capability is also important in healthcare. For example, another of our work presenting in this year's ISMA demonstrated how to bring contouring delineation process of radiotherapy treatment planning into VR. Therefore, it is important to understand humans' drawing ability in virtual reality. To address this, many prior research has focused on evaluating the performance of what we call precision-first 3D drawing, which refers to a drawing process when precision is prioritized over speed. For example, the existing work has focused on evaluating the drawing performance of 1D, such as a line, and 2D, such as a planar circle, in virtual reality. Some works also focus on the drawing performance of what we call combined 2D tasks, such as a cube. Few other works also focus on the 2.5D tasks, such as a planar circle projected on a curved surface. However, there is still a lack of understanding of how humans drawing performance of the true 3D curve, which could only be described by three orthonormal bases. In this work, we focus on evaluating participants' drawing performance with a target tracing experiment of a 3D helical curve, as it is one of the simplest continuous curve with a constant curvature and slope. And it has also been widely used in many existing computer-aided design tools. Mathematically speaking, a 3D helical curve could be described by a parametric equation with respect to a constant, curvature, and slope, noted here as K and S. With this observation, we therefore designed a within-subject experiment with 12 participants. We considered 4 independent categorical variables, including orientations, curvatures, slopes, and input methods. For orientation, we considered 3 possibilities: the up-down, left-right, and forward-backward. We also considered 3 possibilities for curvature and slopes, respectively. Theoretically speaking, the larger the slope is, the more stretched the helical curve will be, and the circle of the projection on the XY plane will have larger radius for the smaller curvature. Then, we also considered 4 input methods, including using a commercially available VR pen and VR controllers, bare hand pointing, and also hand pinching. We then prototyped our testbed on HTC Vive for controller and pen, as well as Oculus Quest 2 for the bare hand inputs, due to a merit of hand tracking performance on Oculus Quest 2. We set up the experimental environment in a typical office room with 2 base stations for tracking purposes. During the study, participants will first complete the pre-study questionnaire, followed by the designated drawing tasks, as well as the post-study experience evaluations. While completing the task with each input methods, breaks were intentionally added to minimize the impact of drawing fatigue. After putting on the headset, participants could complete the designated target tracing tasks, whose order have also been counterbalanced. So how do we evaluate the drawing performance quantitatively? First, we consider the mean overall deviation as a way to measure the drawing precision in spatial domain. Mathematically speaking, the mean overall deviation is simply the average of Euclidean distance between each sample stroke to a target trace. And obviously, a good drawing performance results in a small mean overall deviation. We also consider what we call the number of local maxima of stroke deviations, or NLM in short, in spatial domain. Essentially, this quantitative value describes how frequently the participants attempt to correct the instantaneous drawing errors. We finally also look at the mean drawing speed in temporal domain, which is the average of ratio of Euclidean distance between two consecutive strokes and their time differences. The first part of our evaluation focuses on the main effects. While looking at 4-input methods, it is clear that using a VR pen could generate the highest precision, which might be caused by the higher frequency of error correction attempt. More interestingly, while participants were instructed to perform precision-first 3D drawing, they attempted to draw slightly slower while using the VR pen. When it comes to curvature, we found that the larger curvature could actually generate higher precision. Although such geometry characteristic might also slow down the drawing process. While slope does not necessarily have impacts on the drawing precision and speed, a smaller slope will slightly increase the number of local maxima of errors. Finally, our study also demonstrates a higher precision for forward-backward and left-right orientations. While gathered plenty of insights from the analysis of interaction effects, we would also love to highlight a few exciting findings. First, we found that while being compared to the controller, the VR pen generates more precise drawings, but only at the larger curvature tasks. In addition to that, we found the VR pen demonstrated a more significant precision drawing merits while being compared to the controller for left and right orientations. Finally, we also analyzed the impacts from 3 intermediate variables. There includes the stroke shoulder distance, the absolute instantaneous drawing speed, and drawing precisions. Notably, while participants were instructed to conduct precision for 3D drawing, it is challenging to control and regulate such variables to a desired value. As you can see here, we show the correlation of each of the causal links. In particular, we would love to highlight that with VR pen, the input tools that could potentially achieve the highest precision. The minimal error was achieved when the stroke shoulder distance is around 60% of the forearm length, and when the drawing speed is around 2 centimeters per second. While discussing with participants during post-study semi-structured interview, we generate 5 findings. First, while using VR pen could be more precise, participants think it is also yield high level of fatigue. Second of all, participants also believe that while using hand input could decrease the level of fatigue, the potential reasons vary among pinch and point gestures. Thirdly, occasional occlusions and occasional pull hand trackings are also highlighted as another reason for decreasing the level of confidence. And fourthly, the median curvature and slope was suggested by participants to yield the best delineation experience. And finally, participants also emphasize several opinions regarding the interaction effects between curvature and orientations. Through our quantitative and qualitative findings, we generate our design recommendations in terms of two aspects. The first type of a recommendation focuses on pre-session design stage, which refers to a strategy that could be adopted before each drawing session. For example, designer could use a VR pen as a tool for precision-first 3D drawing. And the issue of occlusion might be one of the key aspects for increasing drawing accuracy. The second type of design recommendation focuses on in-session stage, which refers to strategies that could be integrated during each drawing session. For example, the information of fatigue, drawing speed, stroke shoulder distance, and hand tracking accuracies could be visualized in real time to help users better regulate the drawing postures. Potential feedback also include the scale and orientation, which demonstrated by our finding have impacts on the drawing precisions. As a brief conclusion, we would love to highlight our findings from three aspects. First, VR pen and controller lead to an average of nearly 30% of precision gain, and in particular, VR pen itself yields nearly 50% of more precision than controller. In addition to that, the larger curvature for backward and left-right orientation allows a higher precision of 3D drawing. Finally, we wish our work will benefit future research and to create useful toolboxes for precise 3D drawing and beyond. Thank you so much for the time, and please refer to our paper for more detail.